Okay, so let's look at some thermal processes. So, on your quiz, the very last question was about some thermal processes. And so, if we have a container of gas, and usually you're going to think of it as being a cylinder that has these particles in it, and we've used syringes that had like a piston or a plunger. So you imagine the piston plunger type deal here, and your particles are all in here and they're zooming around. Okay. Now all those little collisions will cause a pressure on the walls, and then there's a particular volume to this container, and the pressure times volume should be equal to the number of moles times a gas law constant times the temperature in Kelvin, right? Now, we talk about changing the system, compressing the gas to a different volume, okay? So let's look at a couple of different ways we could possibly do that. How could we reduce the pressure so we could raise the piston, which would be expanding the volume, so we could increase the volume?
Decrease the temperature.
Is that another option, or is that what's going to happen too?
No, like if it happened to, then the pressure would change it. This is like a different option.
Okay, so we could increase the volume, or we could decrease.
Well, if you increase the volume, wouldn't the temperature like momentarily change and then kind of destabilize?
So when we increase the volume, what's going to happen to our temperature?
It'll drop.
Well, what kind of container do we have?
Cylindrical.
It's a cylindrical container. What's it made of?
Glass.
Glass?
Some solid.
So is it an insulator?
Oh.
Like, is it surrounded? No. So it's in contact with the environment around.
Right.
So, you've got like big fat air molecules. I'm just making it up. So the little purple represent the environment around it. So if it's uninsulated, then if I stretch out that volume, that's going to reduce the pressure. What's going to happen to the temperature?
It'll stabilize eventually.
Equilibrium.
It'll drop, and then it'll go back up, and it'll reach equilibrium with the environment. So if it's uninsulated, okay, the temperature will remain constant.
It was like, remember when we were like compressing it, the temperature would rise and then it would stabilize.
Yep. So if we look at it for that short change, then there's some stuff happening, and our temperature does have a change. But if we let it equilibrate with the environment, it'll reach the same temperature. Now, how could we decrease the temperature?
Put it in an ice bath?
We put it in an ice bath. Okay. So if I put it in an ice bath, and it's uninsulated, because that would be key, right? Because what do I want the ice bath to do? I want it to cool it. Okay. Do you know how to cool something?
Putting something cooler than it already is.
Because what does everything in contact with everything else want to do? Like the natural state is to do what? To be in equilibrium. So even though the top of the table feels cool to the touch, and maybe your calculator doesn't feel quite as cool, or your lunchbox doesn't feel quite as cool, or the wood side of the table doesn't feel as cool, they're all actually in thermal equilibrium because they're all in this room and they've been in this room all day. Okay. Why does the table feel cold? Is because it has a different conductivity. So the table allows energy to be conducted through it, so the energy flows or moves from a high energy state to a lower energy state. If you are at a greater temperature than the room, which you are, then you are warming the room around you.
If I'm in the process of warming the room, how can the room be in equilibrium?
Well, you're not at equilibrium with the room. The room is trying to get in equilibrium with you. Okay, that's perfect. So when we decrease the temperature, we could put it in an ice bath, and what would then happen? What would happen to the volume?
It would stay the same.
So we'd have to fix the piston.
Mm-hmm.
Okay, so we can do several different things to cause a change in temperature, to cause a change in pressure, to cause a change in volume. So just by asking you how we could reduce the pressure, you change something else. So I could ask you how could we decrease the temperature, and you could reply in terms of the pressure. I could ask you how could we increase the volume. You could reply in terms of temperature or pressure. Excuse me. So there are several different processes. First, let's look at a pressure versus volume graph. Okay, so if we have a gas and it's initially at P naught and V naught, and it expands at a constant pressure to P naught and to V naught. What did the piston do? So go back. It went up.
Yeah.
Okay. So if you've got that piston kind of image in your brain there, where this is the piston, and we expand the volume, pretend like I can make these exactly the same pictures every time. It's so not. But then maybe the piston is up here next, and so the volume has increased. So this would be V naught, and this will be 2 V naught, and the motion was up. Okay, so what did the piston do to the environment, the surroundings, these purple dots that represent the environment around it? Pushed them up. Okay, so when you pick up an object and you apply a force in the positive direction and you're moving it in the positive direction, do you remember what we call that? Work. Okay, so if work is force times distance and pressure is force per area, so that means that force is pressure times area, then work would be equal to pressure times area times distance. And area times distance is volume. And so the work done would be the pressure times, and the only way you're going to get a volume is if this is a change in distance, right? So we have to have a change in volume. So the work done by the gas on the surroundings is positive, because the piston pushed up on the particles, the little purple particles in my picture. The piston pushed those up. So the gas inside the container did positive work on the surroundings. So what was the work done on the gas during this process? Negative. So the work done on the gas is negative P delta V. And that is the standard sign that's used on the equation sheet for AP Physics 2. So this is the work done on the surroundings. So in terms of the graph, how could you find the work done on the gas? Oh, I heard it. The area under the curve. And then you would insert the negative sign. Perfect. So the work done on this gas would be negative P naught times V naught, right? Okay. Yep.
I'm not sure.
All right. So this process where the pressure remained constant is called isobaric. Barometer, bars of mercury, iso, same, baric. So that's where that term comes from. Okay, so in order for us to, maybe we have another pressure versus volume situation, and our system starts out at P naught, V naught, and the pressure increases while the volume stays the same, and we go to a final pressure of 2 P naught. How, well, yeah, okay, so there's no area under the graph. So the work done on the gas would be equal to what?
0.
There's no work being done by the gas or on the gas. But the pressure is changing. How can we increase the pressure and keep the volume the same? PV equals nRT, right? So we're going to increase the pressure, keep the volume constant. So what do we have to do to the temperature of our sample? Increase the temperature, which means that what has to increase? What's temperature related to? The average kinetic energy of each molecule. How do you change temperature?
Make work. Yes.
Yes, but it's a word you don't want to use. It's the 4-letter word, heat. You can heat the gas. And so I'm glad that you said work, because heat in thermal processes is similar in meaning as work is in mechanical processes. So work changes energy, heat changes energy. Okay?
So work changes kinetic energy and heat changes, like, specifically thermal kinetic energy?
Thermal energy, yeah.
So it's just a type of work.
It's a type of energy transfer. Only way to change that temperature is to add energy to the system. And the only way we can add energy is, what did we do with the flask with the gas in it? How did we add energy to the system? Yeah, we used the you did heat it up. That's fine. You heated it up. That was perfect. So we can heat the gas. Okay, so heating the gas is a method of energy transfer. Where did that energy come from? The hot plate has a coil inside it that's transferring, yes, with resistance. So our electrical energy is being transferred, like friction inside there, and they heat up. Okay, the molecules inside the coil start hitting each other even more, and so then energy is then conducted, right, through the metal plate, through the glass, through the water, and into our flask. Was kind of the mode there. All right, so we can actually add energy to the system by heating. Okay, so heat is not a type of energy, it is a type of energy transfer. Just like work is not energy, it's a type of energy transfer.
Isn't the work though just a change in energy?
Yes,
So,
work can change energy.
wait, I thought it was a measurement of the change in energy.
Yes, and it is also the measurement of the change in energy. So we can actually define heat as being like work. Okay, work was measured in joules, right? We can measure heat as the amount of energy transferred.
So that would be joules.
Uh-huh. I think that needs another R, but whatever. And that would also be in joules.